Today's adventure is on projectile motion. Imagine yourself riding on a bicycle while chewing on some gum. And midway through your ride, you decide to spit your gum directly vertically upwards. Interestingly enough, the gum will fall back into your mouth again. And this doesn't matter if you're riding your bike rather slowly or if you decide to zip by your bike rather quickly. As long as you're traveling at a constant velocity in a straight direction while doing this, the gum is guaranteed to go back into your mouth. So why does this crazy thing happen? Well, even though we may know that the velocity of the bubblegum in the vertical direction may slow down as it goes up and speed up as it goes back down, something does remain constant, and it's its horizontal velocity. So the inertia of the bubblegum horizontally remains fixed. In fact, since you're riding on a bicycle traveling at a particular velocity, these two objects share the same horizontal velocity, and that's why the bubblegum will always make it back into your mouth again. So how do we deal with these projectile calculations? Well, we just mentioned that Vx is always fixed. And Vy is constantly changing, and that's due to gravity. So Ay is always equal to negative 9.81 meters per second squared. Lastly, the time it takes for you to ride across this road is the same amount of time for the bubblegum to travel up and all the way back down again. In other words, the time in the x dimension will be the same as the time in the y direction. So instead of calling it delta tx and delta ty, we'll just call time delta t from now on. Armed with this knowledge, let's get started. All right, first question in the homework. Helicopter's flying horizontally with a velocity of 25 meters per second. All right, and it drops a parcel 15 meters down below. First thing we want to do is that we want to incorporate a coordinate system. And as a standard practice, we usually like to define upwards as positive and forwards as positive as well. Now, this object will hit the ground because of gravity, so that's why we probably want to deal with the y dimension first. So we'll start off with our givens in the y dimension. We know that acceleration in the y dimension is equal to negative 9.81 meters per second squared. And since this parcel is being dropped, initially in the y dimension, it's at 0 meters per second. You can imagine yourself letting go of a pencil. The moment that your hand opens up, the pencil is initially at 0 meters per second, and then it speeds up and falls down. That's another important thing. If upwards is positive, then downwards is negative. So your delta dy has to be negative 15 meters. And since we already have three givens in our y dimension, we could solve for Vf, and we can also solve for time. In this case here, we want to solve for time, as the time it takes for the parcel to fall is the same amount of time as it takes for the parcel to travel horizontally across. So, given the setup over here, we have to use this kinematic equation. Delta d is equal to Vi delta t plus 1/2 a delta t squared. It may seem intimidating at first, but luckily Vi, since it's 0, that whole term disappears. So we're down to something a lot cleaner, like this. And as we're isolating for time, we first need to multiply both sides by 2. So we have 2 delta d, divide both sides by a. And lastly, since t is squared, we need to square root both sides. Thus, time is equal to the root of 2 delta d over a. Sub the values in as necessary. So negative 15 meters in the numerator and negative 9.81 meters per second squared in the denominator, and the math should work out. In this case, it takes 1.749 seconds for the parcel to fall. That also gives it 1.749 seconds for it to travel across. So our givens in our x dimension is equal to this. Delta t is equal to our just calculated 1.749 seconds. Our Vx was given in the problem, where the helicopter is traveling at 25 meters per second in the forwards direction. So to figure out its horizontal displacement that the parcel will travel, that is equal to this formula here. D is equal to V delta t. Remember that velocity doesn't change, and that's why we're using this simple formula. We multiply 25 meters per second by the duration of 1.749 seconds, and this parcel will therefore travel about 43.72 meters across. So the helicopter needs to drop off the parcel 43.72 meters before its target point. Here's another question. There's a lovely stuffed animal, and his name is Hobbs, and he decides to toss a bottle. And he throws it in a projectile path that looks like this. So during the projection, he launches it at a speed of 10 meters per second at an angle of 60 degrees above the horizontal. What this initially tells us is that the Vx component can be solved by multiplying the hypotenuse of Vi by the cosine of theta, which is 60 degrees over here, as we're solving for this vector here. So our Vx is equal to 10 meters per second, which is the hypotenuse, multiplied by the cosine of 60 degrees as it's given to us in the question, and that's why our Vx is equal to 5 meters per second. Eventually, we'll need to solve for our Vi in the y dimension, so let's just calculate that right now. Vi in the y dimension is equal to the hypotenuse times, now since VIY is opposite of 60 degrees, we multiply by the sine of 60 degrees. That's a quick shortcut in trying to solve for that side. If it seems like a rush, well, try drawing out a right angle triangle, and you'll see that the equation, when it's rearranged, it will always look like this. All right, let's crunch the numbers in. So 10 meters per second times the sine of 60 degrees, and by memory, this equals 8.66 meters per second. The sine of 60 is always equal to 0.866. Okay, another thing that's been given to us in this problem is that we know how far away the bottle lands. It lands horizontally 10 meters into the distance. So since we have our Vx and we have our delta dx, we can solve for the time that it takes to travel. For proper form, we always start off with our givens. So we know that the ball will travel horizontally at 10 meters, and it'll travel at a rate of 5 meters per second. To solve for time, we'll use the most basic of kinematic problems, one where the velocity is constant, and we solve for time. When we divide 10 meters by 5 meters per second, we end up with a time of 2 seconds. So it takes 2 seconds for the bottle to travel across, and it'll also take 2 seconds for it to travel up and down. So we'll have to recycle this 2 seconds for our givens in the y dimension. Just to let you know, I usually denote anything in the horizontal dimension in red and anything in the y dimension in blue. Resultant vectors will be in green. So we know that the time it takes for it to go up and down is 2 seconds. We just calculated out earlier our Vi in the y dimension of 8.66 meters per second, and since this is happening here on Earth, AY is equal to negative 9.81 meters per second squared. It is often good that in your diagrams you include a coordinate system to tell the reader that towards the right is positive and upwards is also positive as well. Sorry, not to the right in this problem. In this case, it's forwards. Okay, so since we know these three givens, we can solve for either VF or time. So, vertical displacement. And since that's what we're trying to solve for, how much did it displace vertically? Looking at this, we'll need to use this formula here. Delta dy is equal to Vi delta t plus 1/2 a delta t squared. Let's sub the values in. So 8.66 meters per second times 2 seconds plus 1/2 times negative 9.81 meters per second squared times time of 2 seconds. Don't forget to square that as well. And after the number crunch calculations, we find out that our vertical displacement is negative 2.30 meters. What that means is that since the bottle traveled up and down and it fell a displacement of 2.3 meters down, therefore the treehouse is 2.3 meters above ground. All right, number 2 is asking about the impact velocity. So taking a look at the diagram, what we're solving for is this apparent green vector. Now I'm drawing a vector on top of a displacement diagram, and it's just for visual correlation. All right, so there's an impact velocity, and that impact velocity is based upon our Vx, which hasn't changed, and our Vfy, which now has changed. All right, remember the bottle slows down as it goes up and speeds up again in the opposite direction as it falls downwards. And that's why our next part is to solve for our Vfy. So what is our Vfy? Again, it's based upon the same givens as above. In this case here, our ideal formula is Vf is equal to Vi plus A delta t. So 8.66 meters per second plus negative 9.81 meters per second squared times the duration of 2.0 seconds. This will give us a Vfy of negative 10.96 meters per second. Just for clarity, let's draw the impact velocity vector one more time. So this is your Vf as a vector. That's based upon two parts. Your Vx, which still remains at 5 meters per second, and your final velocity vertically, which now we've calculated out that it's falling at 10.96 meters per second. So to solve for your Vf, as this is the hypotenuse, we need to use the Pythagorean theorem. Vf is equal to Vx squared plus Vf in the y dimension squared. So that's equal to the square root of 5 meters per second quantity squared plus, you could put down the minus sign, it doesn't matter, but it's effectively a magnitude of 10.96 meters per second quantity squared. Crunching through these numbers, you end up with a final velocity of 12.04 meters per second. Again, impact velocity is a vector, so we need to find out what the theta is. And according to this triangle over here, the theta is equal to the tan inverse of our opposite over our adjacent. The opposite side is our Vfy, and our adjacent side is Vx. So theta is equal to the tan inverse of, now it's up to you whether if you include the minus sign or not. Remember that the formula originally does have absolute symbols on the side. So you don't really need to have that negative sign in the calculation. If you do include it, you'll just find out that your theta is negative, and all that really means is that the angle that you have is underneath the horizontal, which is true. So 10.96 meters per second divided by 5.0 meters per second will give you an angle of 65.4 something degrees. I think 48 degrees. All right, so as a final statement, our impact velocity, or our final velocity, is equal to 12 meters per second forwards, 65 degrees underneath the horizontal. You could also state it as forwards 65 degrees down. That is acceptable as well. A ball is fired from a cannon inclined at 40 degrees above the horizontal. So let's just sketch that on top of this diagram here. All right, so it's projected an angle of 40 degrees above the horizon. That way we can figure out what our horizontal component is and what our vertical component is. Remember that our horizontal component always remains fixed, so it's called Vx, and Vx can be calculated by multiplying the hypotenuse, which is Vi, times, and according to this picture, Vx is beside 40 degrees, so that's where we're going to multiply by the cosine of 40 degrees. Even though we may not need the number right now, we'll just go through the crunching because at some point we probably do need it. So since Vi is equal to 35 meters per second, we multiply by the cosine of 40 degrees, that will give us an answer of 26.81 meters per second. We're going to rinse and repeat for V in the y dimension. Remember that in the y dimension, the values are constantly changing, and that's why we want to denote this as Vi in the y dimension, as our Vf will be a completely different value. So Viy is equal to the original Vi multiplied, in this case over here, since Viy is opposite of 40 degrees, we're going to multiply it by the sine of 40 degrees. So 35 meters per second times the sine of 40 degrees will give us an answer of 22.50 meters per second. All right, so those are some preliminary calculations we want to deal with. In part A, it's asking us how high does it reach, or how long will it take for it to reach its maximum height. So what do we know in the y dimension? Just to make our lives easier, we probably want to include a coordinate system so the reader knows that up is positive, and I guess this is our forwards direction, and we'll denote that as positive as well. So we know that when an object reaches its maximum height, VF goes to 0 meters per second. VI in the y dimension, as we're only looking at the vertical component, it was traveling at 22.50 meters per second. Remember, only the vertical component is influenced by gravity. That's why we're only looking at the 22.5 as opposed to the full-blown 35. So AY is at negative 9.81 meters per second squared, and part A is just asking for the time it takes. Here we need to pull out this formula. And again, after enough practice, you can rearrange these things easily in your head. So VF is 0 meters per second, VI is 22.50 meters per second, and A is at negative 9.81 meters per second squared. Luckily, since the numerator and denominator are both negative, we end up with a positive answer as expected. So the time that it takes for it to reach its maximum height is 2.293 seconds. Now, even though it's true that it'll take another 2 more seconds for it to travel all the way back down again, so in other words, you can probably estimate that the total time is roughly 4.5 seconds, I'd rather not use that shortcut. Instead, let's solve this problem using a different perspective for B. So, what do we know? We know that initially it was launched vertically at 22.50 meters per second. It's going to slow down as it ascends because of gravity. The acceleration due to gravity is at negative 9.81 meters per second squared. So it starts from ground, and it's going to finish at ground again. If you compare the height at the beginning versus the height at the end, you'll find out that your delta dy has not changed in height. You started from ground level, and you finished at ground level. And that gives you the sufficient 3 givens. All we need to solve for is time. So we'll need to pull out this kinematic equation. Delta D is equal to VI delta T plus 1/2 A delta T squared. Initially, this may seem intimidating, but luckily, since one of the terms goes to 0, we don't have to use the quadratic formula in solving this. Now, depending upon your teacher, you may be required to carry the units throughout the remainder of the calculations, and if you do work it through that way, believe me, the units will work out. In this instructional video, after our first substitution of the units, we'll drop the units afterwards. We know that time will be measured in seconds. So 22.50 delta t minus 4.905 delta t squared is equal to 0. And when we factor out time, we can quickly find out our 2 roots. One of them, as you can see immediately, time is equal to 0. As for the second one, we know that 22.50 minus 4.905 delta t, this term here also has to go to 0. So when you rearrange for this time here to make it equal to 0, that's equal to 22.50 divided by 4.905, which will give you 4.587 seconds. So even though you'll notice that, yes, your final answer is double of the initial, by solving the problem this way, you can cover all cases. So in other words, if this cannonball so happens to land into a ditch that's 10 meters below the horizon, you can use this formula. If it lands on a tree that's 3 meters tall, you can use the same formula. You can't exactly double the time if it falls on something slightly higher, because it'll take less time for it to fall than for it to rise. Okay, so if we know that it's going to take 4.58 seconds for it to rise and fall, we have the same amount of time for it to travel horizontally. So that's our last bar. We'll start off with our givens. We know that our Vx is equal to 26.81 meters per second, and we just calculated out the time that it remains airborne is 4.587 seconds. So the horizontal range is equal to this formula here. So a constant velocity of 26.81 meters per second multiplied by a time of 4.587 seconds will give you a horizontal range of initially 122.98 meters. And just approximating with our givens here, since our givens are 2 sig fig, our final answer is probably going to be 2 sig fig as well. Some textbooks will just leave it as 120 meters, but just to keep it consistent, we'll just write in scientific notation. So 1.2 times 10 to the 2 meters, and universally everyone will know that this is an answer that's only 2 significant figures. The reality is that in any sort of projectile motion, if you just change your projection angle, even up to 40.1 degrees, you know your outcome's going to be different. That's why you cannot guarantee that your final landing place will be exactly at 122.98. There are so many other factors that can influence it, so that's why your final answer is probably going to be approximated. In this case over here, someone decides to throw a parcel off one building and it lands on a second building. What we do know is that the second building is located 100 meters away. Now, it is possible for the parcel to land on a taller building, but it is also possible for a parcel to land on a lower building. And we won't know if the second building is taller or lower until we get to that point in our calculations. So let's go and figure out what's going on here. This person decides to launch a parcel at a velocity of 20 meters per second at an angle of 15 degrees above the horizontal. With this brief sketch over here, we can solve for our Vx and our Viy. Again, it's probably best to just deal with these calculations from the beginning since you'll most likely need both values at the end. So our Vx is equal to our Vi times the cosine of theta, which is equal to 20 meters per second times the cosine of 15 degrees, and that gives us 19.32 meters per second. Our Viy is also equal to our hypotenuse. This time around, as it's opposite to the 15, we'll multiply by the sine of 15 degrees. So 20 meters per second times the sine of 15 degrees, that will give us an answer of 5.176 meters per second. And just to tell the reader what you're defining as positive, we'll just include this coordinate system here. Up is deemed as positive, and towards the right, we'll deem that as the positive forwards direction. All right, so one thing that we do know so far is that we have two givens in our horizontal dimension. We know that the second building is located 100 meters away from the first building. We also know from our initial calculations that it is traveling at 19.32 meters per second. This is enough information for us to figure out the time that it takes for it to travel horizontally. Remember, there's no acceleration in the horizontal dimension, and that's why our formula for the horizontal dimension is so nice and clean. When we isolate for time, we divide delta dx by Vx, and 100 meters divided by 19.32 meters per second will give us a time of 5.176 seconds. And yeah, this measurement here is coincidental with Viy. Wasn't expecting that, but it worked out coincidentally here. All right, so it takes 5 seconds for it to travel across, which means that it also took 5 seconds for it to go up and down. And now we'll deal with the y dimension. Let's see what we know in the y dimension. We know that our Vi in the y dimension, it was launched at 5.176 meters per second. Gravity is pulling the parcel down at negative 9.81 meters per second squared. And yeah, we do know that our displacement of our building is at 200 meters above the ground. All right. In other words, that's our initial position. Sorry, that is our initial position. All right. And we're trying to look for our final position. That's what we're trying to solve for. So looking at all the stuff here, oh, we also have time. I almost forgot about time. Of 5.176 seconds. That was given from before. We can solve for our final position. So the formula that we'll be using is delta D is equal to Vi delta T plus 1/2 A delta T squared. Carefully sub the values in. And don't forget to square your time. Crunching that through our calculator, we'll find out that our delta D is equal to negative 104.6 meters. So what exactly does this mean? Remember, the picture that I have on the right is for representation purposes only. It looks like the second building seems to be rather short. The second building is 104 meters lower than the first building. Keeping in mind that delta D means that you're measuring between your final minus your initial position. So if we really want to find out our final position or the final height of the second building, we need to take our DI, or the initial height of our first building, and add it with the delta D that we calculated. So since the first building is 200 meters tall, and now the parcel has dropped 104.6 meters, what this tells us is that the second building is 95.38 meters tall. So a fighter jet is going 350 kilometers per hour, and it dives at an angle of 25 degrees, but this time around it's to the vertical. So just keep in mind that the angle in this problem over here is measured this way. What that tells us is that our Vx is going to be equal to our Vi times the sine of theta. All right. I know that's very tempting to say that Vx is equal to Vi times cosine of theta, but really the choice between sine and cosine is based upon your diagram. Similarly, when we're trying to solve for our VIY, that in this case over here is equal to our hypotenuse of Vi times, and as this is adjacent to the 25 degrees, we multiply it by the cosine of theta. All right, now we could use the VI value of 350 kilometers per hour, but then we're going to have unit problems afterwards. So we're going to do the quick shortcut. We're going to convert 350 kilometers into meters per second, and you do that by dividing by 3.6. You could also do it the long way by multiplying 350 kilometers over hours, and know that for every 1 hour, there are 3,600 seconds, and for every 1 kilometer, there are 1,000 meters. This is just another way of getting to the same exact answer of 97.22 meters per second. So the choice is yours. You can either solve it using that longer method, or by knowing that if you need to convert between kilometers per hour into meters per second, all you need to do is divide by 3.6. Okay, I think that's enough knowledge to start solving for our Vx and Vy. So we'll just quickly do those calculations on the side since we need it in the future anyways. All right, so our Vx is equal to 97.22 meters per second times the sine of 25 degrees, and that will give us 41.09 meters per second. And our Vi in the y dimension, if we assume upwards as positive and towards the right as positive as well, then VIY technically is equal to the negative of the hypotenuse of 97.22 meters per second times the cosine of 25 degrees. That way it'll give us an answer of negative 88.11 meters per second. All right, so its initial velocity is pointing downwards. Again, if it wasn't for the ground down below, this activity would just keep on going forever. So we know that this problem will end once it hits the ground. Being that case, we want to deal with the vertical dimension first. So we know that our Vi in the y dimension is equal to negative 88.11 meters per second. Our AY is also equal to negative 9.81 meters per second squared, and our delta dy, as it's fallen downwards at 200 meters. Some of you might notice that we all have minus signs over here, and yeah, it is possible to assume downwards is positive, all right, and it will work out. However, since I assumed upwards is positive, we'll continue with that narrative. When we're trying to solve for time over here, we find out that unfortunately we have to use this formula here, and since t is linear in this term, and t will unfortunately be quadratic in the second term, we'll need to use the quadratic formula in solving this. And to prepare ourselves for that, we need to convert this into standard form, starting from the term of highest degree, downgrading to the one which has a linear term, and then we'll finish off with the constant. Now remember that since I'm bringing delta d over, delta d becomes negative delta d, and all of this will go to 0. That way we can quickly figure out what our a term is, what our b term is, and what our c term is as well. Okay, so it's up to you how you decide to solve this. Some people would like to sub these variables right into the quadratic formula and create a standard equation, but you can also solve this just from what you know so far. And that's what we're going to do. We're going to sub in the values of 1/2 negative 9.81 meters per second squared, delta t squared. We're going to add it with negative 88.11 meters per second, delta t, and we're going to subtract it with negative 200 meters. So you'll see that you have a double negative over here for your c term. All right. So this tells us that our a term is equal to negative 4.905 delta t squared, or sorry, negative 4.905. Our b term is equal to negative 88.11, and our c term, the double negatives, will give us a positive 200 as in meters. All right, so quadratic formula is negative b plus minus the root of b squared minus 4ac, all divided by 2a. Sub the values in. And if you're wondering, could I include the units in here? You absolutely could. In fact, I'm sure your teacher would encourage you into doing it. However, since that'll take up too much real estate here, I'm just going to forego that. But trust me, if you include the units in there and you try simplifying this, you'll definitely get your units in meters per second. Sorry, in seconds as it's time. So 2 times a, which is negative 4.905. And you'll find out that there are two roots in this problem. All right, there's a negative root, which doesn't make any sense, and then there's a positive root of 2.038 seconds. And since time can only be positive, this is the only logical correct answer. You got to keep in mind that this fall is based upon the quadratic curve or parabolic curve. In other words, there will be a positive time of 2 seconds where it's touched the ground, and mathematically, because it's a parabola, there will be some negative time where it was also at the ground as well. And that's why you end up getting two roots. Again, the negative time is irrelevant for this problem, and that's why we drop it. Okay, lastly, since it takes 2 seconds for it to fall, that means that we have 2 seconds to travel across. So we'll finish off with our last set of givens. We know that our Vx is equal to 41.09 meters per second. The time that it takes for it to travel across is the same time as it takes to fall down, of 2.038 seconds. So our horizontal range that we need to, or that will land, is equal to v times t. So 41.09 meters per second times 2.038 seconds will give us an answer of 80 something, 83.76 meters. That's how far it will travel horizontally. The last part is asking what will the velocity of the parcel be just before it hits the ground. I guess for that I'll need to clear up some space. Why did I erase all of that? I guess I could have reused my givens. That's okay. Okay, so we could have used the time in solving for our final velocity, but if we made a mistake in our time, then our final answer will be further off from the correct answer. So that's why I want to avoid using that time, especially since it came from this crazy quadratic formula, right, where chances of making a mistake is rather high. Okay, so let's just revisit our givens one more time and see what's another plan of attack that we can do. VIY is equal to negative 88.11 meters per second, AY is equal to negative 9.81 meters per second squared, and our delta dy was equal to negative 200 meters. That is sufficient in solving for our VF. There is a formula for it, and it looks like this. Now remember that when you isolate for VF, when you're square rooting both sides, technically you have two possible answers, a positive answer and a negative answer. Negative 88.11 meters per second squared, quantity squared actually, meters per second quantity squared, plus 2 negative 9.81 meters per second squared multiplied by negative 200 meters. Luckily, the two negatives right over here will become positive so that we have an answer that is solvable. So our VF in our y dimension is plus minus 108.1 meters per second. All right, remember that this is based upon a parabolic curve. So at the beginning of our activity, yes, it was traveling upwards at 108.1 meters per second from ground level, supposedly. And when it hits the ground at the same altitude, it will also travel at 108.1 meters per second, but downwards. And that's why we know that the answer we're looking for is negative. So we have a VF of 108.1 meters per second, and we have a VX that's been fixed since the beginning of 41.09. So to solve for our impact velocity, we need to use the Pythagorean theorem and then use inverse tan in getting to our answer. Sometimes it helps to have a brief sketch. So let's just draw a brief sketch representing the impact velocity. All right, so it's going to hit downwards, and when it hits downwards, it has a horizontal component and a vertical component, and the angle that I'm going to measure based upon this drawing is that theta here. Okay, so we have a known Vx value, and we have a known Vfy value. Okay, so our Vf is equal to the root of Vx squared plus our Vfy squared. Sub the values in. Negative 88.11. If you're one, oh no, not 88, negative 108.1. And if you're wondering, does the minus sign really matter? No, it doesn't, because double negative becomes positive. All right, so you have a VF, which is just the magnitude, and that is 115.6 meters per second. You can convert that into kilometers per hour if you wanted to. As for the angle of VF, according to our diagram, that's equal to the tan inverse of our opposite, which is our Vfy, divided by our Vx. All right, so Vfy is 108.1 meters per second. If you want to put a minus sign there, you could. You'll just end up with a negative answer, and that's because this object is going to hit the ground below the horizontal, and that's why you're going to get a negative answer. So I'm not too concerned about whether if you put the plus or minus sign there, because you'll have to intuitively know that it's going to land below the horizontal anyways. So 108.1 meters per second divided by 41.09 meters per second, you'll notice that the meters per second have to divide each other out because you're looking for a ratio. And the ratio of a triangle, where the opposite side is 108 units and the adjacent side is 41 units, will always give you an answer of, oh man, what is it? 70 degrees? No, 69 degrees. So your VF will equal 115.6 meters per second, forwards, 69 degrees downwards. Another valid answer for this is 115.6 meters per second, downwards, 21 degrees forwards. Either answer is correct. You can also multiply your 115.6 by 3.6. So 115.6 times 3.6 will give you 416 kilometers per hour. 416 kilometers per hour. Now looking at our givens, since our angle is at 2 sig fig, you probably want to round these answers to sig fig as well. All right, we have a lovely little frog, and it holds the whole world record for jumps. When it launches at an angle of 58 degrees above the horizontal, these guys can reach as high, or your delta dy, of 58.7 centimeters or 0.587 meters. Maybe I should draw that in blue because that is a vertical value. Okay, so here's the thing. We know the vertical value of 0.587 is the highest it can jump at its final height. Vf is equal to 0 meters per second. And this frog is bounded here on Earth, so Ay is equal to negative 9.81 meters per second squared. And that's how we have all of our three givens in the vertical dimension. dy yet again is 0.587 in meters. So that will be our givens. Okay, we're going to assume that upwards is our positive direction of travel, and we'll just say that towards the right is also our positive direction of travel. So our Vf is equal to 0 meters per second. Our Ay is equal to negative 9.81 meters per second squared. And since it jumps upwards to a maximum height, that's why your dy is a positive 0.587 meters. With this, we can find out our Vi, and we can also find out the time, which is not important here. So let's just solve for our Vi in our y dimension. So knowing that Vf is equal to Vi plus 2a delta d, where the Vf and i's are squared, when we isolate for Vi, Vi is equal to Vf squared minus 2a delta d, all square rooted. All right, and it is true, Vi could be a positive or negative term, but since we know the frog is leaping upwards, we're taking the positive term while it's going up, not when it's landing. So Vf goes to 0 meters per second, so 0 minus 2 times negative 9.81 meters per second squared times a height of 0.587 meters will give us a Vi of 3.394 meters per second. Okay, let's just draw the projection one more time. All right, so here is our Vi. That Vi has two parts, and we just solved for our Vi in the y dimension. Okay, we also know that the frog, in this case over here, to attain that maximum height, had to leap at an angle of 58 degrees above the horizontal. With this, we can solve for two things. We can solve for our Vx, and we can solve for our Vi. Let's solve for, what are we looking for? What is the takeoff speed? So in other words, we are looking for the big Vi. All right, so we know that the sine of theta is always equal to the opposite, which is VIY, over the hypotenuse of VI. Let's color code that, VIY. And since we're trying to solve for our VI, therefore VI is equal to VIY divided by the sine of theta. So let's go through that. VIY of 3.394 meters per second divided by the sine of 58 degrees will give us a much larger speed of 4.002 meters per second. So that is our takeoff speed. Okay, so takeoff speed of the frog is 4.0 meters per second. And if you're to describe as a velocity, then yes, it will be 58 degrees above the horizontal, if it was a velocity. But since it's speed, we'll just drop the direction. That's not necessary. Okay, next thing is the horizontal range of this frog. Okay, so first we need to figure out the time it remains airborne. So in our givens, what do we know? We know that our VIY is equal to 3.394 meters per second. We know that AY is equal to negative 9.81 meters per second squared. And the last one is just keeping in mind that the frog started from the ground and it finished back at the ground again. So if you take a look at its position vertically at the beginning versus position at the end, we notice that our delta dy hasn't changed. All right, our vertical displacement is 0 meters. That's sufficient information to tell us the amount of time it takes for it to go up and all the way down. Okay, so this equation here, delta D is equal to VI delta T plus 1/2 A delta T squared, and we're going to isolate for time. It may seem intimidating, but luckily since one of the terms goes to 0, we do not need to use the quadratic formula. 3.394 meters per second delta T plus 1/2 negative 9.81 meters per second squared times time squared. Drop the units, factor out T. So one of the roots is 0, and the second root is 3.394, subtract 4.905 T. All right, so one of the T's is equal to 0, and the second one is delta T is equal to 3.394 divided by 4.905. Okay, keeping in mind what we're trying to do is that we're trying to take the term inside and equate it to 0. So once you equate it to 0 and rearrange for time, you find out that the time it remains airborne is 0.6919 seconds. Okay, so it had 0.6919 seconds to travel up and down, meaning it also had 0.6919 seconds to travel across. So the last thing we need to do is to solve for our Vx. Now we could use our Vx based upon our Vi, but just to avoid too much rounding error, let's just solve it the longer way. We know that tan of theta is equal to our opposite of VIY divided by our Vx. So if we're trying to solve for our Vx is therefore equal to our VIY divided by the tan of 58 degrees. All right, so 3.394 meters per second divided by the tan of 58 degrees will give us an answer of 2.1206 meters per second. Okay. So Vx is equal to 2.1206 meters per second. The time it takes for it to travel across is 0.6919 seconds. So our horizontal displacement is therefore equal to Vx delta T. 2.12 multiplied by, I ran out of space, multiplied by 0.6919 seconds will give us an answer of 1.467 meters. Seeing that our givens are 3 sig fig, we'll comfortably state that the horizontal range of this frog is about 147 centimeters. That's how far it can jump. For question number 7, a marble is thrown horizontally with a speed of 15 meters per second. So what do we know? We know the Vx value. Sweet. However, when it strikes the ground, we have this crazy thing going on. It has an impact velocity, all right? And it's an impact velocity that makes an angle of 65 degrees relative to the horizontal. Remember that when it impacts the ground, the horizontal component has not changed, but there is a measurable vertical component. Okay, so what can we figure out right over here? Well, since we have a triangle over here and we know what Vx is and we know what an angle is, it is possible to find our Vf in the y dimension. And that's exactly what we're going to do. We know that in this case over here, that's opposite over adjacent, so we use the tan of theta. So the tan of theta is equal to our Vfy all over our Vx. So when we solve for our Vfy, that's equal to our Vx times the tan of our impact angle. So 15 meters per second times the tan of 65 degrees is equal to 32.168 meters per second. And by looking at the diagram, since it's pointing downwards, we know that it needs to be a negative sign. Okay, so now we have our Vfy. What else do we know? Good question. Well, one thing I just noticed right now is that our Vi in the y dimension is equal to 0 meters per second. Again, this is happening here on Earth, so we know that we have a value for A as well. And that seems like it gives us our three givens. So we can solve this first in our y dimension. We know that our VI in the y dimension is equal to 0 meters per second, as again the marble is thrown horizontally. Our VF, it hits the ground downwards at 32.168 meters per second, and gravity caused this to happen. All right, with that, we can find out the height of the building. Do we care about that? Yeah, the height from how high above the building it fell. And eventually, we're probably going to solve for time as well. So we need to solve for our delta dy, and we will solve for our delta t for part B. We'll deal with the first one right now. What is delta dy? Well, we have a formula that looks like this. Vf squared is equal to Vi squared plus 2a delta d. All right, so when we isolate for delta d is equal to Vf squared minus Vi squared all over 2a. Negative 32.168 meters per second. Quantity squared, subtract 0 meters per second. Quantity squared divided by 2, negative 9.81 meters per second squared. This will give us a negative answer. It'll give us an answer of negative 52.74 meters, which is true. It did fall 52 meters down. What that tells us is that therefore the building is 53 meters tall. Right, as the marble fell 53 meters down. Okay, again, we are going to reuse the same givens. This time around, we're going to solve for time, and that formula will be Vf is equal to Vi plus A delta t. Time is equal to Vf minus Vi all over A. So negative 32.168 subtract 0, units, meters per second, divided by negative 9.81 meters per second squared. And this will give us 3.279 seconds. All right, so it took 3.279 seconds for it to fall. What that also tells us is that we have 3 seconds to travel across. So let's recap in the x dimension. We know that our Vx is at 15 meters per second, and we know that our time for it to fall is 3.279 seconds. So the distance that it'll fall from the base of the building is equal to, let me rewrite it again. Delta dx is equal to Vx delta t. Vx of 15 meters per second times a time of 3.279 seconds will give us a grand distance of 49.19 meters. With our givens of 3 sig fig, therefore the object has landed 49.2 meters from the base of the building. So this horizontal range of dx is equal to 49.2 meters. All right, number 8. A soccer ball is kicked from the ground level at 25 meters per second. All right, so here is our VI projection. It is at an angle of 25 degrees to the horizontal. With that, we can solve for the horizontal component of Vx, and we can solve for the vertical component of VIY. Okay, and yeah, that will end up creating just some generic equations, such as Vx is equal to our Vi as our hypotenuse multiplied by the cosine of theta, and our VIY is equal to our Vi times the sine of theta. Of course, we don't know what the value of Vi is yet. That's what we're trying to look for. Is it? No, we do know it. All right, so let's just go through those calculations first. Vi is equal to 25 meters per second. So 25 meters per second times the cosine of 25 degrees, and that will give us 22.658 meters per second. How many sig figs shall we carry? Well, I suppose we don't need to carry that much at all. If our givens are 2 sig fig, then our intermediate calculations should at most be 4 sig fig, so I'll just stick with that. 22.66 meters per second. We could carry more, but you'll find out that it's becoming less and less computationally efficient as you're going to round anyways. All right, so VIY is equal to 25 meters per second times the sine of 25 degrees. 25 times sine of 25 gives us 10.56. Is that enough? No, 57. 10.57 meters per second. Okay, and that's sufficient. Okay, so staring at it, we're having a tough time right now, aren't we? What do we know? We know that there's acceleration. We know that there's VIY. Oh, and the third thing is that we know that our delta dy, it's going to rise up to a dy of 2.0 meters. I believe that is sufficient to give us our three givens, and that's why I'm going to solve the y dimension first. Okay, because we know that our VIY is equal to 10.57 meters per second. AY is equal to negative 9.81 meters per second squared. And our delta dy, it has risen up to a height of 2.0 meters. And we're looking for time. Okay, so we're going to use this formula. Delta d is equal to vi delta t plus 1/2 a delta t squared. When we sub the values in, oh no, it looks like we need to use the quadratic formula. So 10.57 meters per second plus 1/2 negative 9.81 meters per second squared delta t squared. So just to keep my a term positive, I'm going to bring all the terms over to the left-hand side. So I have positive 4.905 delta t minus 10.57 delta t, delta t squared for the first one. And since 2 meters is already on the left-hand side, it still remains as positive 2 meters, or positive 2 is equal to 0. Yes, you could include the units here, and you could sub it into the quadratic formula. Negative b plus minus b squared minus 4ac, but it is a very long way of getting to the answer, and it will work. It will work. It will work out to seconds. All right, so we sub the values in. So negative 10.57 plus minus the root of 10.57 times, or 10.57 squared, subtract, 4 times 4.905 times a c of positive 2. Divide that all by 2 times 4.905. This should give us 2 positive roots. Did I calculate that out here? Ooh, there's my cheat. Okay, my 2 possible answers is 0.210 seconds or 1.944 seconds. All right, so you might be wondering, oh man, I got 2 positive roots. What's going on? Well, if you look at the original picture, and you know that this line over here represents 2 meters, there are 2 instances when you've reached the 2 meter mark. One of them is, yes, when you landed on the tree itself, but another incidence of when it reached the 2 meter mark is at the beginning of the activity. So that's why there are these 2 routes. One route is at 0.2 seconds while it's rising, and the second route is at 1.9 seconds when it's finally falling. And since we are looking for when it lands on the tree, we know that we can't take the first value because that's while it's rising. We want it while it's falling, and that's why we're going to use 1.944 seconds as our delta t. Okay, so I don't want you to ignore the first one, but just know that the first one is for its rise time, and we're only concerned about its fall time because it's going to land on the tree in the distance. Okay, so it takes 1.944 seconds for it to rise and fall, and we want to figure out how far away is the tree. So look at our givens in the x dimension. We know that Vx is equal to 22.66 meters per second. Our time for it to travel is a total of 1.944 seconds. So our dx is equal to Vx delta t. 22.66 meters per second times 1.944 seconds is equal to 44 meters. 2 sig fig? Yes. Delta dx is equal to 44 meters. End of story. Now, for the remainder questions, when we get there. Now, for the remainder questions, they are challenging questions. All right, so let's just briefly talk about how would we solve these questions. All right, without going through the long calculations. So a golfer strikes a golf ball at 17 degrees above the horizontal. That we know. And we're wondering how hard must he hit it so that it can reach 250 meters in total. All right, so for a delta dx of 250 meters at the end. Okay, now we don't know what the value of VI is. That's what we're trying to solve. So when we start with our givens and our formulas, what we'll notice is that, yes, we do know our delta dx, and our Vx is just equal to, and we've calculated this before, our Vx is equal to our Vi, and since 17 degrees is adjacent to it, it's just simply Vi times the cosine of theta. That's where I got this part from. This does lead us to an equation with two unknowns, unfortunately. We don't know what Vi is, and we don't know what delta T is. We could isolate for either of them for now, and as a heads up, isolating for time is the more efficient way of solving this question here. Okay, and in our y dimension now, we have to use this equation here. Again, it's going to rise and fall back to the same height. So our dy goes to 0. So 0 is equal to VIY delta t. Again, our VIY is equal to our VI, and as it's opposite of 17 degrees, that's why we're going to multiply it by the sine of 17 degrees. Again, that's where we got this guy here from. Okay, and once we sub it in, we get something that looks like this. Now, these are two equations with two unknowns, so why don't we just sub one into the next? Right, and it makes more sense to sub equation 1 into equation number 2, and I've already isolated equation number 2 for VI. So you sub them in, carefully crunch it through, and then you'll figure out what your VI is. So that is the initial speed. These are more challenging questions as you end up having two equations with two unknowns, so you have to solve linear problems by either substitution or elimination. And substitution is often the easier way. Number 11 probably shares the same fate, where what do we know? Well, its horizontal range is what? 60 meters. Okay, so we know that our dx is 60 meters. We know that its fall is 30 meters. We also know the projection angle, which is at 40 degrees above the horizontal. All right, so it's very similar to the previous question. In the vertical dimension, we'll use this kinematic equation here. VIY is equal to VI times the sine of 40 degrees. A we know as well. We know that's going to fall 30 meters. All right, again, in this problem here, we're assuming that upwards is positive and towards the right is positive, and that's why it has fallen 30 meters. Okay, at this point over here, what can we do? Nothing. We have an equation with VI, delta t, and delta t squared. So it's an equation with two unknowns. One of the unknowns is linear and quadratic. So we just leave it alone. In the horizontal dimension, we know the value of dx already. It's 60 meters. So 60 meters is equal to VI times delta t. Our VI is equal to VI times cosine of theta. And again, we're stuck on an equation with two unknowns, VI and delta t. So we can isolate either for VI or for delta t, and my recommendation in these questions here is to isolate for VI. And the reason for that is that if you isolate for time, you're going to be subbing it in twice, and that's going to be pure madness. So if you isolate for VI, you'll see that the units do quickly clean up, and you can quickly solve for time. So it'll take 4 seconds for it to go up and all the way down. And if we know the time it takes for it to go up and down, we can figure out other things as well, such as its initial muzzle velocity of 19 meters per second. Make sure you show all your work when you're solving this. And I believe this is the last part over here. If we know that our VIY is 19.35 meters per second times sine of 40, which is this value over here, and at maximum height, it's going to pause briefly. We can first figure out what our delta dy is. In other words, what this part is. And with that solution there, we need to add an additional 30 meters afterwards. So you'll calculate it through, add an additional 30 meters to get to your final answer. In this question, we have a cute little kitty cat. There's Meow Meow right there. Why not? And the kitty cat sees a lovely little spider in the distance and it wants to pounce at it. Now, you'll notice that in this question over here, it tells us the impact velocity. In other words, the velocity it strikes the spider at, which is at 10 meters per second. Now, when it strikes it, it hits it at an angle of down 30 degrees forwards. So down 30 degrees forwards. Okay, so our angle is measured right over here for our 30 degrees. What this tells us is that our Vx, as its opposite of the 30 degrees, our Vx is equal to our Vi times the sine of 30 degrees. So Vx is equal to 10 meters per second times the sine of 30, which is equal to 5 meters per second. We can also find out our Vf in this problem here. Okay. Our Vf, and it's a Vf in the y dimension, that is equal to our hypotenuse of Vi, and because it's beside 30 degrees, times the cosine of 30 degrees. I know it's tempting to reverse them around because you're used to seeing it the other way, but that's why it's always relative to the angle that's measured, not relative to some arbitrary triangle. Okay, so 10 meters per second times the cosine of 30, and since the cosine of 30 is always 0.866, if we multiply that by 10, we get 8.66 meters per second. Keeping in mind that because it's pouncing downwards, this would be in a downwards direction of negative 8.66 meters per second. Okay, so what do we know so far? Well, we know that the spider is located 1.38 meters away horizontally. All right, so we have enough information to start solving this in the x dimension. We have a dx of 1.38 meters. We have a vx of 5.0 meters per second. So if we're trying to solve for time, we'll take this formula and isolate for time. So the time for it to take for the cat to pounce downwards is equal to dx divided by vx. All right, so 1.38 meters divided by 5.0 meters per second gives us a fractional time of 0.276 seconds. Okay, so the cat has 0.276 seconds for it to travel down and pounce on the spider. That will also tell us the distance that the cat will have to fall. Now, there's no guarantee that the cat had a VI of 0, all right? So VI, we have no idea what it is, okay? It does not have to be, not necessarily 0, okay? It doesn't have to be it. So instead, let's just take a look at what we do know so far. We just calculated out that the time for the cat to go downwards is 0.276 seconds. We know that A is equal to negative 9.81 meters per second squared if we assume upwards is positive and forwards is positive. Lastly, we did calculate out this negative 0.866 meters per second. So that is important, and that is a VF. And VF is equal to negative 8.66 meters per second as he's pouncing downwards. With this, we could solve for two things. We can solve for delta D, and we can also solve for VI if we wanted to. All right, and as I said, VIY doesn't necessarily have to be at 0, so you could calculate it if you want to. But we'll just leave it with delta D. Okay, so we'll have to use this unique formula, which is VF delta T subtract 1/2 A delta T squared. This is different than the formulas we've used in the past, as this one deals with the final velocity. So negative 8.66 meters per second times a time of 0.276 seconds minus 1/2 negative 9.81 meters per second squared and a time of 0.276 seconds squared. When we calculate through this, we'll have a fall of negative 2.02 meters. And since the cat has fallen 2.02 meters, therefore, this special type of bookcase, where if you look on IKEA, this is known as the Billy brand. So this Billy bookcase must be the type of bookcase or bookshelf that the cat jumped off of. Wasn't that fun? For more adventures like this, make sure you do your homework. Catch you later.